Here at the Post Mortem Files, we give clear, factual breakdowns of not just what went wrong, but why. Each video examines a failure, collapse, or critical decision through calm analysis, timelines, and cause and effect. No hot takes, no hype, just the post-mortem. On the morning of June 18, 2023, a support vessel sat on the surface of the North Atlantic. The ocean looked calm enough for operations. Far below, roughly 3,800 meters down, about 2.5 miles, the wreck of the Titanic rested in darkness. At that depth, the pressure outside any submersible is immense. Every square inch of the hull experiences thousands of pounds of force pressing inward. Inside a submersible named Titan, 5 people prepared to descend into an environment that does not negotiate. Down there, the difference between working and catastrophic is not gradual. It is binary. Either the pressure hull holds, or it does not. Within about 2 hours of the start of the dive, Titan stopped communicating with the surface. If you followed the news in real time, you probably remember the sense of a ticking clock. Oxygen estimates, search grids, the question of whether this was a communication problem, a power problem, or something worse. In a post-mortem, we do not start with guesses. We start with the system, what it was designed to do, what it was exposed to, and what decisions shaped the risk long before the final dive. Titan was not an unmanned prototype. It carried people. That matters because when lives are inside the machine, the acceptable level of uncertainty changes. The people on board were there for reasons that are easy to understand. Curiosity, exploration, the draw of history. The Titanic wreck is a powerful symbol, and seeing it in person is something only a few hundred humans have ever done. The dive was not presented as a one-off experiment. OceanGate had conducted previous expeditions to the Titanic site. There were briefings. There were procedures. There was a routine. Routine shapes how people perceive risk. When something is done repeatedly without incident, it begins to feel controlled, even when the environment itself remains unforgiving. OceanGate Expeditions was built around a thesis. That deep-sea exploration had become too slow, too expensive, and too constrained by conservative practices. Traditional submersible programs require long development timelines, heavy certification, and high costs. OceanGate's leadership believed those constraints limited progress. Titan was designed to move faster. It was intended to be lighter than conventional submersibles, cheaper to build, and easier to modify between missions. This was not just an engineering philosophy. It was a business model. More dives meant more missions. More missions meant more revenue. When speed and cost efficiency are central goals, engineering trade-offs are evaluated differently. In extreme environments, those trade-offs directly affect how much uncertainty the system carries. At the heart of Titan's design was the pressure hull. The pressure hull is the structural shell that keeps the occupants alive by resisting the immense external water pressure. Traditional human-occupied submersibles rely on thick metal pressure hulls made from steel or titanium. These materials are heavy, but their behavior under repeated loading is well understood. Engineers can model how metals fatigue, meaning how they weaken over time when stressed repeatedly. Titan used a carbon fiber composite pressure hull with titanium end caps. Carbon fiber composites are materials made from strong fibers embedded in a resin. They are lightweight and strong, especially under tension, which is when forces pull along the fibers. Deep sea pressure creates compression, which squeezes the structure inward from all directions. Composites behave differently from metals under repeated compressive loading. Internal damage can accumulate without obvious external signs. 2 common damage mechanisms are microcracking, which refers to tiny internal cracks, and delamination, which is when internal layers begin to separate. This kind of damage can progress beneath the surface while the exterior still looks intact. Each dive subjects the hull to a pressure cycle. A pressure cycle is one full loading and unloading of the structure as it descends and ascends. In metals, engineers can estimate how many cycles a structure can endure before fatigue becomes dangerous. For composite pressure vessels under deep-sea compression, long-term fatigue data is limited. This does not mean composites cannot be used. It means there is more uncertainty, about how quickly their structural margins degrade over repeated cycles. Pressure testing can demonstrate ultimate strength, which is the maximum load the structure can survive at least once. It does not fully characterize fatigue behavior, which is how the structure changes after many cycles. A bridge that can hold a heavy truck once may still fail after millions of lighter loads. The same principle applies here. Geometry also matters. Titan's hull included interfaces between different materials. The junctions between the carbon fiber cylinder and the titanium end caps are regions where stress concentrates. Stress concentration means that forces become higher in small areas than in the surrounding structure. Over time, these regions are more likely to initiate damage under repeated loading. In the deep-sea industry, human-occupied vehicles are typically certified by independent classification organizations. Certification does not mean nothing can go wrong. It means the design has been reviewed against conservative safety requirements, tested against defined margins, and assigned inspection protocols. Safety margin refers to extra strength built into the system beyond what is strictly necessary for normal operation. It is a buffer against unknowns. OceanGate did not pursue full third-party certification for Titan. Leadership argued that existing certification frameworks were too slow and not designed for rapid innovation. Instead, safety validation was conducted internally. This reduced development friction. It also reduced the number of independent challenges applied to foundational design assumptions. Over time, this influenced organizational culture. When external safety standards are framed as obstacles rather than safeguards, the baseline for acceptable risk shifts. This process is known as normalization of deviance. It means that conditions that would normally be considered outside conservative limits become accepted because nothing bad happens immediately. As Titan conducted more dives, each successful mission reinforced confidence. In high-risk systems, success can be misleading. The absence of immediate failure does not mean the absence of degradation. With each dive, the hull experienced another pressure cycle. The internal condition of the structure likely evolved in ways that were difficult to measure non-destructively. There were reports from earlier dives of unusual sounds during descent. In engineering terms, these can be described as acoustic emissions, which are noises produced when small internal changes occur in a structure, such as microcracking. Hearing such sounds does not automatically mean imminent failure, but in composite structures under extreme pressure, they can indicate that internal damage is occurring. When such signals repeat without immediate consequences, they can become background noise rather than warning signs. By the time Titan began its final descent on June 18th, the mission felt routine. Communication with the surface support vessel was maintained during the early phase of the dive. There were no public indications of immediate trouble. Approximately 1 hour and 45 minutes into the descent, communication was lost. There was no distress signal and no gradual failure reported. Search and rescue operations were initiated. For several days, attention focused on possible scenarios and oxygen timelines. When debris was later found on the ocean floor near the Titanic wreck site, it confirmed a catastrophic implosion. An implosion is the rapid collapse of a structure when external pressure exceeds the structure's ability to resist it. At extreme depths, this happens faster than human perception. There is no progressive failure phase that occupants could respond to. From a systems perspective, the final dive did not introduce a new category of risk. The environment did not change, the depth did not change, the pressure did not change. What likely changed over time was the remaining structural margin after repeated cycles of loading and unloading. The Titan disaster was not caused by a single mistake. It emerged from interacting decisions made over time, a material choice that introduced uncertainty into a high-pressure environment, a validation approach that emphasized iteration over independent review, an organizational culture that framed established safety standards as constraints, an operational history that normalized anomalies and reinforced confidence. Each of these decisions, taken alone, did not guarantee failure. Together, they formed a pathway in which the system's ability to absorb unknowns gradually eroded. In extreme environments, failure often feels sudden because the erosion of margin happens quietly. The people who boarded Titan trusted the system they entered. That trust was shaped by routine, by prior successful missions, and by the way risk was communicated. Their decision to descend was made within a system that presented the operation as controlled and repeatable. In the deep ocean, innovation must be paired with validation at least as aggressive as the environment itself. The ocean enforces physical limits without regard for intent. It rewards margins, verification, and humility. Here at the Post Mortem Files, we examine failures to understand the pathways that lead to them. The Titan disaster was not a random accident. It was the outcome of a system that gradually narrowed its margin for survival. This has been the post-mortem of the Titan submersible.